the last session, we studied separately excited DC generators. Today, we'll start with shunt field DC generators. As you know, in case of a shunt field DC generator, the field winding is in shunt with the armature winding. You do not have a separately excited field source. This is your armature resistance. It is in parallel with the shunt. It's in parallel with the field winding. So you have the armature resistance here. You have the field resistance, field inductance, EA, and available to us is the terminal voltage of this machine. So as we know, armature current will be in this direction, the field current will be in this direction, the line current will be in this direction. So from the looking at the KVL equations first, so as we have EA firstly, IA is equal to IL plus IF, or in other words we can say the line current will be equal to IA minus IF. Second thing here to note is that EA is equal to VP plus IARA, which implies VT is equal to EA minus IARA. We need to plot VT versus IL. We can therefore say EA minus, instead of writing IA, we can write IL plus IF RA. So before we plot this VT versus IL graph, or VT versus IA graph, what we need to know is, in case of a DC motor, we were basically applying the terminal voltage, and this terminal voltage, that means current would flow in the system and IF would flow in the system. Why? Now, once IF would flow, that means the magnetic field would be produced in the system. This current would also flow through the armature. So you had a current carrying conductor placed in the magnetic field that would basically experience rotation, and the principle of operation was fine. We had a current carrying conductor placed in the magnetic field. It would experience torque, and therefore the shunt field DC motor, it would work easily. Now in case of, same was the case with series field DC motors. Now in case of shunt field DC motor generators, now you can see we have the prime mover attached to EA that's actually rotating this device. So we have a rotating conductor, but there is no magnetic field. Why is there no magnetic field? Because IF will not be flowing. Because IF work, there needs to be a voltage in this system, and there is no voltage yet generated in this system. That means there is no current flowing through the field windings IF, and since no current is flowing, there is no magnetomotive force produced by the field windings. So you have seen only a rotating conductor. You have no magnetic field, so no voltage will be induced. Now how to basically get that magnetic field? So what we see in case of DC generators is that there is some amount of residual flux left over in the field windings. So this residual magnetic flux, because of this residual magnetic flux, EA A phi residue omega, we are having normal omega, residual flux will be very small. Even if the motor is rotating at is made to rotate at greater speed, 100 rpm, 1000 rpm, 2000 rpm is fine. Residual flux will be very small. It should be sufficient enough to even produce a voltage of 1 to 2 volts. Fine. So once this voltage is available to us, this voltage will cause current to flow through the field windings. Once this voltage is available, only because of the presence of some residual magnetism left over in the motor, in the machine, this from some previous operation, so this voltage will be sufficient to induce IF, that's current to flow through the field windings. Once the current will flow through the field windings, it will increase the flux. Once the flux will increase, EA will again increase. So this process will basically continue. It will again increase IF, that will again increase flux, that will again increase EA, that will again increase IF. So in other words, we can say, if we plot EA versus IF graph first, there is a small residual magnetism because of which EA residue is produced, and this flux will be increasing, and as soon as field current increases, EA will increase until flux saturation occurs, and then this becomes the voltage remains constant. Flux no longer increases, that no longer increases the motor voltage. So this is actually voltage build up in a DC generator, in a shunt DC generator. What happens is that because there is no field, we should expect no voltage to be generated, because we only have a rotating device. We do not have any field, we do not have anything else to make the current to voltage to induce in this motor. Because of some leftover flux from the previous operation, even if that's of the order 0.0001 Webbers, it will be enough to induce a voltage of 1 to 2 volts that will cause current to flow through the field windings. It will produce a little bit more flux, that will produce a little bit more EA, that will produce a little bit more current to IF. So this process will keep on happening. It can explain basically through a feedback mechanism. So EA will eventually build up as IF increases. So in this case, unlike the separately excited DC motor, in case of a shunt DC motor, the voltage built up is not instantaneous. It takes some time. Now at times you basically see, even if you apply the voltage to a shunt field generator, not voltage. If you rotate the shunt field DC generator, you are through the prime mover, the voltage is not induced, voltage is not built up in the DC generator. So what are the possible reasons in that case for voltage build up? Voltage build up does not take place sometimes. What can be the reasons? One, absence of residual magnetism. So this happens if you are operating the motor, the generator, the DC generator, after a long time, whatever flux value was there, that has been long lost, and it will not be available there. Or sometimes it can be phase reversal. That means the connections are actually reversed. So instead of increasing the flux, what happens is that if there was a residual magnetism, residual flux component available in the DC generator, but because the connections have been reversed, instead of increasing the flux, it will decrease the flux, and it will make the flux from, even if it was 0.001, it makes it to 0. So instead of increasing it, it will make it to 0. So once it becomes 0, then there is no scope of voltage build-up. So that is another possible reason. Third possible reason can be the resistance of the field windings. Fine, if the resistance of the field winding is large enough, that will actually make IF very small. So that might not be sufficient enough to produce a flux in the because we are only producing a 1 to 2 volts of 1 to 2 volts of EA is being generated by the residual flux. So if RF is very large, IF that will flow through that will be very very small. So it will not be able to produce the flux in the machine. So RF has to be less than the critical value of resistance. So there are some these are some of the issues that can occur with the DC generator, the shunt field DC generator, because of which the voltage buildup will not take place in the DC generator. For um, getting rid of this problem that I discussed here, that's of no residual magnetic flux being present in the system, what we can do is we can basically flash the fields. So what that actually means is connect it to a this is known as flashing of for solving this issue, for addressing this issue. What we do is we flash the fields. Flash the field means connect the DC winding, connect the field winding to a DC battery. Momentarily. So connect this momentarily so that DC voltage will flow to the field winding, that will produce a flux, and current will start to flow through the field windings. And for making sure that phase reversal does not cause any problem, make sure that your connections are your connections are appropriate. You have not made connections in the opposite manner, or if their phase reversal now occurs, again flash the fields in the reverse direction so as to make sure that the voltage build-up takes place, and also make sure that your field this actually will be the design problem. The field resistance has to be less than the critical resistance of the motor. So this is about DC voltage buildup in DC shunt generators. Going back to the terminal characteristics, we have this equation: VT is equal to EA minus IL plus IF RA. VT is equal to EA minus IL IL IF that's VT is equal to EA minus ILRA minus IFRA. We have to plot VT versus IL. So again, just like the separately excited DC generator, this is IL. We're not plotting against IA, we're plotting IL at IL equal to 0, and we cannot say IF is 0. IF has to be there for EA to occur, but let's assume IF is 0. So this will start with at a point where VT is equal to EA, and then there will be a drop because of ILRA. Fine. So this will, instead of writing ILRA, we can say this is IRA drop, and there's second drop because of the flux weakening. Fine. This is basically portion refers to the flux weakening portion. As you increase the field current in the motor, as you load the as the IL increases, it also basically increases the field current through the field windings. So field weakening will also occur simultaneously in the motor. So there are two drops. Unlike the separately excited DC motor, you have both the IARA drop. This is actually the ILRA drop, but I'm writing this as the IRA drop. And secondly, we have the field weakening effect in this motor because of IFRA. This is not something you can, this drop is not similar to, it's not something that you can see in the separately excited DC motor, but this is only available in the shunt DC generator. So there is a drop because of the current flowing through the armature resistance that will contribute to IRA drop, and because of which the terminal voltage will decrease. And secondly, the terminal voltage will also decrease because of the increase in the IL increases, that actually in turn increases IA also, because IL is equal to IA is equal to IL plus IF. So IL increases means IA increases, IA increase means IRA increases. So if IRA increases, that means VT decreases. Fine. So this is one thing. Now if VT decreases, since we know this field current IF here is equal to VT divided by R. So if VT decreases, IF decreases. So with VT decreasing, IF decreases. So simultaneously IF is also decreasing. So if IF decreases, that causes the flux to decrease. If flux decreases, that causes EA to decrease. If EA decreases, that again causes VT to decrease. Right? So this is a simultaneous process. So this will continuously take place. This field weakening effect is much more sharp in case of a DC shunt generator as compared to a separately excited DC generator. And this is your speed, this is your terminal characteristics of shunt generator. Now the final in this, we have the terminal voltage control of a shunt generator. Just like in case of separately excited DC motors. Voltage control method. Voltage control in shunt generators. We can achieve voltage control. We have again the same two methods. You can use flux. You can control EA by flux or by omega. Omega is limited because of limited prime mover control. Flux you can change by changing RF. So you can incorporate more, and you can have an adjustable field winding so that IF can be increased or decreased accordingly. Flux can be increased or decreased. That in turn increases or decreases EA. That in turn increases or decreases the terminal voltage. So this is all about the shunt DC generators. In the next session, we'll be doing the series DC generators.